Today we're going to be learning about conic sections still, but we're going to be talking about the parabola. And that may seem a little odd because we've studied parabolas, but we have studied the quadratic function. And so when we were studying the quadratic function, that actually is a different definition for a parabola. There is another definition for the parabola, and so we want to talk about that. We are again talking about conic sections. So to be the geometric definition, if we're thinking about how does it interact with the cone, the geometric definition is going to be the cone being sliced by a plane. So we're still looking at a cross section, but we're looking at a cross section that is going from the side of the cone into the bottom of the cone. And so it's going at an angle through the sides of the cone. So it doesn't actually go in one side and out the other like the circle did. Remember, the circle had to be parallel to the base and it entered in one side and went through the other. The parabola is going to enter in from one of the sides and go down into the base, and it gives you that parabola cross section. So that is the geometric definition of it. So it's the plane intersecting the cone so that it goes through a side and through the bottom. And that's what makes it a parabola. Now, there is an algebraic definition of this geometric shape, and it's all the points that are equidistant, remember that means same distance, from a given line, which we call the directrix, and a fixed point that is not on the directrix of focus. All right, so when we talk about the algebraic definition, remember the algebraic definition of the circle was the set of points that are all equidistant from one single point. A parabola is going to be the set of points. So again, you're talking about that edge, that set of points out here that are the same distance from a line and a point. So instead of all being the same distance from one point, they're the same distance from a line and a point. So let's look at that definition and what everything looks like. So any point on the parabola are these points that we're talking about. It's the set of these points. These are the points that are part of the algebraic definition. The line that it is measured from and its focus that we're measuring, we're equidistant from it. Is that any given point is going to be the same distance from the line as it is from the focus. Now remember, when we measure a point's distance from a line, we are talking about a perpendicular distance. So for any point on the parabola, if you go vertical, perpendicular to this directrix, that distance has to be the same distance as from that point to the focus. So that means that these two distances are the same. That's the equidistant part. Now, it doesn't mean that every point has the same distance. So notice the green point. Its distance from the focus and the directrix are the same for that point, but it's obviously not the same distance as this point. So it's not equidistant in a circle in that every point is the same distance from the focus. That's not what is equidistant. What is equidistant is that every point on the parabola has to be the same distance away from this line as it is from this point. So this gives us equal distances for each point between the line and the point. All right, so you have a focus and you have a directrix. So items referenced on the graph of a parabola. All right, these are things that some we are familiar with. The vertex. You guys know what the vertex of a parabola is. We've used that before. It's where it turns, where it stops being decreasing and it becomes increasing. So that's the vertex. The directrix is new. And I do want to point out this should be a dashed line. It's not actually part of the graph, so you want it to be a dashed line, like the axis of symmetry. You guys have worked with the axis of symmetry before. Interesting things about the axis of symmetry is the axis of the symmetry and the directrix are perpendicular to one another. All right, so if the directrix is horizontal, the axis of symmetry is going to be vertical. If the directrix is vertical, the axis of symmetry is going to be horizontal. We'll see what that looks like in just a second. Because we are not dealing with functions, we're dealing with a geometric definition of it, I can have a vertical directrix, which would mean that my axis of symmetry is horizontal and my parabola can actually go to the side. I can have a sideways parabola because we're not talking about the function definition of a parabola. We're talking about the geometric version of the parabola. And so it's all of these points that are equidistant from a focus and a directrix. And so we can have a focus over here and a directrix that is vertical, and then we can have the parabola go in this direction. So you can have sideways parabolas, which is something we've never seen before. But these are the parts of the parabola that you always want to show up in your graph. So here's some facts about parabola equations. In a parabola equation, one variable is squared and one is not. All right. Think about the circle. When we were working with the circle yesterday, x was squared and y was squared. But now only one of them is going to be squared. There are many different ways the equation of a parabola can be written. We will get to the quadratic part, the variable part, on the left side of the equal sign, and the linear part, the one that's not squared, on the right side of the equal sign. And when you do, you get an equation that looks like these. So either your x is going to be squared, or your y is going to be squared. One of them is squared, one of them is not. All right. Now, some things that are similar to yesterday. Notice h and k. They're both exactly where they were yesterday. H is with x and k is with y. And that is because just like yesterday, hk was the center. It was the defining point of the circle. hk is still the defining point of the parabola. It's just that it's not a center, it's the vertex. Okay, so hk is still going to be our defining point. All right, the vertex, it's going to be very important. And h, the number that is with x, is always the x coordinate, and k, the number that is with y, is always the y coordinate. And just like with the circle, we always do the opposite of that number inside the parentheses with the x or with the y. So that part is exactly the same as with circles, and in fact is consistent through all conic sections. The important defining point is always hk. H is always with x, the x coordinate is always with x, and k, the y coordinate, is always with y. It always stays together, and we always do the opposite. So that part is staying the same. What you're also going to notice here is we have this p value, and p is very important because p is the distance from the vertex to the focus. All right, so P is the distance from the vertex to the focus. And that is important. So we've got our distance from the vertex to the focus, P, and we've got our vertex. And this is actually enough information that we can graph a parabola. So we just have to have it in the correct form. Now, notice that technically there's kind of two forms because, again, one version is if the x is squared, and one version is if the y is squared. So what is the difference if x is squared and y is squared? So let's talk about what that does to the graph. So we have our two versions, either the x is squared or the y is squared, and the other is not. All right. So what that means for us, if we look down here, how do we decide which way the parabola opens up? And that has to do with which one is squared. All right, that's the first thing that we're going to want to look at. If x is squared, that's the one we're used to. We're used to doing parabolas with x squared. If x is squared, the parabola is either going to be opening up or the parabola is going to be opening down. That's the parabola we've always done. Y equals and x is squared. So that's the one we know. If x is squared, it opens up or it opens down. And it's our p over here that tells us which one is which. If p is positive, it opens up. And if P is negative, then it's going to go down. Positive is up, negative is down. So that means if y is squared, then we're going to have a parabola that either opens to the right or we're going to have a parabola that opens to the left. Now, just like with P up here, up was positive and down was negative, to the right is positive and to the left is negative. So P, positive or negative, is still going to tell us which of those two that we're dealing with. So when we're graphing, we always want to make sure we figure out which one is our squared term, because it's going to tell us, are we dealing with an up-down parabola or are we dealing with a left-right parabola? Now, once we have figured out what direction our parabola is supposed to be facing, we just need to find all of the parts and get them put where they belong. So the first thing that we want to locate is the vertex. So we'll go to HK. Remember, opposite of the number that's with X and opposite of the number that is with Y gives us our vertex. And so we want to put the vertex on there. The next thing we need to figure out is where is the focus that goes along with this vertex. And that's why we needed to know which direction our parabola was supposed to be opening, because that's the direction that the focus is going to be from the vertex. So if my parabola is supposed to be opening up to the right, then I'm going to make sure that my focus is P spaces away from the vertex in that direction. If it's supposed to be going down, I'm going to make sure that my focus is that direction from the vertex, because the focus is always inside the parabola. If your vertex is that point where it turns around, the focus is inside of the parabola. So that's why we need to know which direction it's facing. So then we can have our focus and we can have our vertex. And once we have our focus and our vertex, we can actually draw the axis of symmetry. The axis of symmetry is going to go through both the vertex and the focus. So our axis of symmetry goes right through wherever our vertex and our focus is. And so then we will have that axis of symmetry. So now we know what cuts our parabola in half. Now, once you have your vertex and you have your focus and you've drawn your axis of symmetry, we need to figure out where is our directrix. Now, the beauty is once you have your vertex and your focus and you've drawn your axis of symmetry, so you have a vertex, you have a focus, the directrix is the same distance away that the focus is. It's that P value. It's just that wherever your focus is, we need to go the opposite direction on the axis of symmetry to get to the directrix. So I'm going to go that same distance. I'm just going to go in the opposite direction. And also, the directrix is not a point. You know, our focus was a point, but our directrix is not a point, it's a line. And specifically, it's a line that should be perpendicular to the axis of symmetry. So we'll have that axis of symmetry. We come over the same number of spaces, whatever that P was, we go to the other direction, and that's where we're going to put the line that's going to cross perpendicular to the axis of symmetry. So now we have a vertex, we have a focus, and we have our directrix. And then we need to actually draw our parabola. And to do that, we need a couple of more points. See, right now we only have one point that's actually on our parabola. We only have one point that is part of that set of points that are all the same distance. And so what we're going to use is this idea that a point on the parabola has to be the same distance from the focus as it is from the directrix. And so if I have a point that is this distance here, 2p, right? If it's 2p going up this way, that means that it's going to have to be 2p away from the focus as well. And so I want to actually draw, and we have a cool little name for this. It's a chord that's going to go through the parabola. It's going to touch the parabola in two places. and it's always going through the focus. And what's interesting about that chord, it's got a nice Latin name, latus rectum focal chord. It is always going to be the width 4p. That's actually where that number in the equation comes from. It's the width of this chord. And so I'm going to take this distance 4p and I'm going to put it on the focus. Now I need to split it in half. So 2p is going to go on this side and 2p is going to go on this side. But that's going to give me a point on this side of the parabola and a point on this side of the parabola, because now I'll have 3 points that actually fit on my parabola. And so once I have that focus, that focal chord, or the latus rectum, okay, once I have those 2 points, I have 3 points, which gives me a very nice curve that I can use for my parabola. And so that's kind of the process that we want to go through when we're graphing one of these. So let's look at an example. So example number 1. X minus 5 squared equals 12 times y minus 6. So we mentioned that the first thing we want to find is our vertex. So I'm going to find my vertex. I know it's the opposite of the number with x, so that's going to be positive 5, and the opposite of the number with y, so that's going to be positive 6. So that gives me my HK. So I'm going to have a vertex at 5, 6. The next thing that I need to figure out is, what is my P equal to? I want to find P. These are kind of the important things. So what we want to remember is this coefficient number up here is not P. It's 4P. So 4P is equal to 12. That means that P must be equal to 3. So we always end up taking that number and dividing it by 4. To figure out what our p-value actually is. And that's an important number to have, because it's going to help us find the focus. It's going to help us find the directrix. We use it to find that latus rectum, to find the other 2 points. So it's really important. So let's start using this information to actually graph. Now, before I can go any further, I want to know which direction. Actually, I probably should have figured this out first. What direction is my parabola going? So I notice that x is squared. So that means that it's either got to be opening up or it's got to be opening down. And since this 4p, this number right here, is positive, p is a positive number, that means that it must be opening up. So this is going to be an up and down parabola. So I'm going to go to the point 5, 6. 5, 6. And that's going to be my vertex. Now, since I know that my parabola is opening up, that means I want to go up 3 spaces, 1, 2, 3, to get to my focus. So I have my vertex and I have my focus. Now I can use these 2 points to draw my axis of symmetry. So this yellow line here, I'm making a dashed line. It's the axis of symmetry. And now that I have that axis of symmetry, I want to take P and I want to go the opposite direction. So that's going to be 1, 2, 3 this way. But I'm going to put my directrix here. And I know that my directrix is perpendicular to the axis of symmetry. So now I have my directrix. Now, oftentimes you'll be asked to write the equation for the axis of symmetry or the equation for the directrix. So for my axis of symmetry, this is a vertical line. So that's going to be x equals, and x happens to be equal to 5 because it does go through the vertex. For my directrix, that's a horizontal line. So that's going to be y equals, and it looks like that line is at 3. So y equals 3 is going to be my directrix because that was 3 spaces below the vertex. Now for the last little bit, we need those 2 other points so we can draw our nice parabola. And so we need to find that latus rectum. So to get that focal chord, I need to know what was 4p equal to. 4p was equal to 12. So I need a segment that's 12 wide here at F. That means I need to go 6 out to the right. 1, 2, 3, 4, 5, 6, and 6 out to the left. 1, 2, 3, 4, 5, 6. So that's going to go right here. So that gives me the width, so to speak, of my parabola. This 12 is the width for those 2 points there. So now I can draw a nice curve to go through and give me my nice parabola shape. So I have a focus, I have a directrix, I have an axis of symmetry, I have a vertex, and I have the 2 endpoints to that focal chord so that I get a nice shape to my parabola. Another example. So looking at this example, we've got y plus 3 squared equals negative 4x minus 2. So the first thing I notice is that y is what is squared. So that means that it's going to be going to the left or to the right. And when I look here at my 4p value, it's negative. So that means that I have a negative p, so it's going to be going to the left. So I know that this is going to be a left-facing parabola. So now I want to find my vertex. All right, guys, it's x is with x and y is with y. So it doesn't matter which side of the equation that it actually ends up on. I'm going to do the opposite of the number with x, so that will be positive 2. And I'm going to do opposite of the number with y, so that's going to be negative 3. And that means that our vertex is going to be at 2, negative 3. After we find our vertex, we need to figure out what is our p equal to. So we know 4p is equal to negative 4. So therefore, p must be equal to negative 1. So again, the negative just told us which direction that we're going. When we start talking about quantities, don't forget it's always the absolute value of p. We're just interested in the actual amount of p, which in this case is just going to be 1. So now we want to start actually drawing our graph. So we have a vertex at 2, negative 3, which is going to put our vertex right here. Our focus needs to be 1 away. So I'm going to mark it so I don't get confused which one's my vertex and which one's my focus. And we know that our parabola is supposed to be facing to the left. So 1 to the left is going to give me my focus. Now, that means that my axis of symmetry goes right through both of those points. So this is going to give me my axis of symmetry. And my axis of symmetry, since it's a horizontal line, is going to be y equals, and it looks like right here, it goes through negative 3. Now, we also know that p, the distance for p to the right, is where our directrix goes, and the directrix needs to be perpendicular to the axis of symmetry. So since the axis of symmetry was horizontal, my directrix is going to be vertical. And so for my directrix, I get x is equal to positive 3. And so now all I'm missing is that focal chord so that I can actually get those other 2 points and I can draw my parabola. So since 4p, the absolute value of 4p is equal to 4, because again, we're just interested in the quantity, not the direction, I need to put a chord that is 4 long on the focus. So I'm going to do 2 on this side and 2 on this side. So that gives me that nice focal chord that is 4 long. And that gives me the other 2 points so that I can draw a nice curve through those other 2 points. And this gives me the graph of my parabola. Now, just like with the circle, the problem we run into is that not every equation is actually in graphing form. Sometimes they give us the problem in standard form, and we are going to have to put it in graphing form because what we have determined is that standard form is not very useful. And so we want to make sure that we can take it from standard form and put it into graphing form. The good news is that the steps are pretty much identical to what they were for a circle. The first step is going to be to organize the equation. Yesterday, we wanted to get all the x's and the x squareds together and all the y's and the y squareds together. Today, it's more about separating the squared variable from the non-squared variable. So when we organize our equation today, we want the squared variable and all of it. So if it's x squared, we want the x squared and the x. Or if it's y squared, we want the y squared and the y. But we want the squared variable on the left side of the equal sign and the not squared variable and the constant on the right side of the equal sign. So whatever we need to do, if we need to add it to both sides, subtract something from both sides, but if we need to move things from one side to the other, we want all the squared variable stuff to be on the left side, and we want all the not squared variable and the constant to be on the right side. So get organized first. Second step is actually still going to be to complete the square. The good news is you only have to complete the square once this time because we only have one squared variable. So that one left-hand side, we're going to need to complete the square, but we're still going to have to remember whatever we add to one side of the equation, we have to make sure that we add it to the other. So we want to make sure that we add to both sides of the equation. But we're going to complete the square just like we did yesterday. And then just like with the circle, after we've completed the square, the next step is to factor. Because again, that was the point of completing the square. We want to factor this side so that it's a binomial squared. But we're also going to have to factor the not squared side of the equation. If you recall, looking at whatever variable was over here and wasn't squared, it has to have a coefficient of 1. So that means whatever the coefficient is in front of this variable, we're going to have to factor it out of the binomial because this has to have a coefficient of 1. So we're going to organize, we're going to complete the square, and then we're going to factor. So let's look at an example. So I have the following equation, and I want to graph it. The problem is it's not in graphing form. So that means I can't actually find anything useful from this equation. So I want to get it into graphing form. So first, I'm going to organize. I want to get all of my squared variables on the left-hand side. And then I want to get my non-squared variable over to the other side. So this is going to be negative y squared minus 4y, and then it's going to be equal to negative 2x plus 6. Now the problem with this is we can't complete the square if this is negative. So I do actually want to go through and multiply everything by -1. So I'm still organizing here. Some people would rather at this point, they're just going to move the 6 over to this side and then rewrite it so that the squared variables are on the left and the non-squared variables are on the right. So that's another way of thinking about doing the same thing, but we're organizing. So now I'm going to multiply everything by -1. So I end up with y squared minus 4y is equal to 2x minus 6. So I've gotten all of my stuff organized. And after we organize, our next step, we said, was to complete the square. So when we complete the square, don't forget it's b over 2 squared. That's what we want to add to both sides. So -4 divided by 2 squared is going to be -2 squared, which is just +4. So I want to add +4 to both sides. Again, I can't just add it to one side. I have to add it to both sides. So I completed the square. And then the last thing that we want to do is we want to factor. Now, over here, I did need to go ahead and simplify. What is -6 plus 4? -6 plus 4 is just going to be -2. So that did simplify to 2x minus 2. But now we want to factor. So when we factor y squared minus 4y plus 4. We said when we complete the square, the point of doing that is that this b over 2 number is always what it factors to be. So that'll be y minus 2 squared. But on this side, we're always going to have to factor out whatever this leading coefficient is. So I want to factor out that 2. I want to undistribute it and move it back up to the front. So that's going to leave me with x minus 1. And that is actually my graphing form. And that would be enough information for me to actually figure out what I'm supposed to do here. So my y is squared. That means that it's going left and right. It's positive, so it must be going to the right. I know that I have a vertex at opposite, positive 1, opposite, positive 2. I know that I have a p-value. 4p is equal to 2. Therefore, p has to be equal to 1/2. So that distance from the vertex to the focus and the vertex to the directrix is just going to be 1/2. And then I can find everything that I need to actually graph that parabola.